So when we're talking about embedded devices and microcontrollers, what does OpenMRNLite really work well on? It works well with CAN bus support, a large variety of STM32s. So the F0, F1, F3, F4, F7, L4, these all work well. The G0, the G0 will not work at this point. G0 has a different CAN bus controller. The ESP32 also works well. You can take the regular, the S2, the C3, the H6, whichever you have. Those have relatively good APIs. So all of these work very well. And I have recently made the port for the Adafruit Feather M4 CAN Express. This has a 32-bit SAMD microcontroller, and the really big benefit is that it actually comes with the CAN transceiver as well. So you only need to screw in the wires. In addition to this, OpenMRNLite is going to work well with serial or Wi-Fi on pretty much any 32-bit Arduino core. So you take a Uno R4, a TNZ3, a TNZ4, a Pico, almost all of the feathers, not the original ones. Anything with SAM or SAMD, NXP, Mbed, TIVA, PIC32, it works on PIC32. Even the older ESP8266, it's gonna work. The only thing is that if you want CAN bus, then you will need to provide a driver for that. However, what it doesn't work and will never work, those are the 8 or 16-bit processors. So like none of the AVRs, like not on the original Uno, not on the Nano, anything that's AVR based, not on the Mega, the 80, CAN 90, all of these, it's not going to work. It's also not going to work on PICs, like PIC12, PIC16, PIC18, PIC24, all of these are 8-bit microcontrollers. It's not going to work on a DSPIC either. That's a 16-bit processor core. So this is kind of like important to keep in mind when looking at what kind of hardware you're looking at. Obviously, some Arduinos have 32-bit processors. Other Arduinos don't have 32-bit processors. And that's basically the boundary of where OpenMRN is going to work or where it's not going to work. And then there is another important note about how much program space is there on your Arduino. You really need to have at least 128K. OpenMRN is not going to fit in 64K. And I basically recommend you to have 256K of flash. So try to look for boards that have at least 256K of flash. This is kind of like a sweet spot. There are lots and lots and lots of options. So what's the problem with the CAN bus really? For the CAN bus, we need a very, very, very simple API for CAN bus. And this is the API that you will find on most Arduino things, including like the serial drivers. So you need to have read, write, and then you need to have available and available for write. So obviously read and write will read a frame from the queue. Write is going to put a frame into the queue. Available has to return non-zero if there is an incoming frame that came and it's in the queue. And available for write has to return non-zero if your outgoing transmit buffer is not full. If you have space in the output buffer, available for write needs to be able to know that. Now, if we look at the real CAN bus, sort of like the CAN bus drivers or these CAN bus libraries for Arduino, they are written in extremely varying quality. Some are really good, some are rather poor. Almost all CAN libraries are missing the available for write method. So that's really kind of like a make or break point for you, unless you're willing to go and patch the library. This available for write is kind of like a tricky question. If your particular CAN controller has an Arduino library that has available for write, you're good. You can make it very, very easily connected into OpenMRNLite. You really need to write only these 4 functions. Unfortunately, with some of the rather poor Arduino CAN libraries, you're completely lost and hopeless. Like I have seen a CAN library where the write frame function call had an 8,000 cycle sleep in there in order to wait roughly about a millisecond or so, at the end of which it basically said like, oh, I think it's not going to be transmitted on the CAN bus. So it is pretty clear that whoever wrote that 8,000 cycle sleep was absolutely clueless about how CAN bus works and how the arbitration control works and how to write reasonable transmit and receive buffers and how to ensure that you don't have a buffer overrun. The reason that we actually require all four of these methods is that OpenMRN takes extremely good care not to run out of memory. So there are a lot of processes in OpenLCB that heavily rely on the prioritization of the CAN bus. And OpenLCB is designed from day zero on to be able to operate at 100% bus utilization. This is a big difference to, for example, LocoNet. In LocoNet, if you have more than 50% bus utilization, everything just crashes and burns. OpenLCB is designed to run at 100% CAN bus utilization, which also means that all implementations, correct ones at least, of OpenLCB need to make sure that they understand whether and when and how many of the packets that they want to send have actually made it to the bus during arbitration. So this is why we require all four of these commands for CAN bus. Now, the supported microcontrollers like the STM32, the ESP32, the SAMD, I have them. So these are fully covered. So those work very well. If you want something new, then it's going to be your responsibility. If you do contribute, let me know, and I'll upstream it into OpenMRNLite. I would be very happy to extend this list of supported boards. So how do you actually go and write a sketch with OpenMRNLite? I mean, this is basically the simplest sketch that you can ever write in OpenMRN. This is for an STM32. So you basically just, you're declaring components at the global namespace. You create the OpenMRN object that's going to be your node ID over there. Here you basically tell to add the serial driver as a port with Grid Connect protocol. So this is going to be the computer interface that sends your text packets, your CAN frames in text packets to and back from the computer. Then this is going to be the CAN bus port. The particular driver, you tell which pins are the CAN TX and CAN RX. This is for something for the STM32 because there are many options there. And you basically just tell the OpenMRN object that here is a CAN port for you. You do that in the setup, you do it once. And then once you've done that, you basically just tell OpenMRN to begin and loop. So that just runs the OpenMRN stack. So when you have added more than one interface to OpenMRN, OpenMRN will automatically mirror all the CAN frames between the two interfaces. So this actually created a CAN USB adapter here behind the background. And by the way, it's also going to be an OpenLCB node, so it will be visible in the node browser, and you will be able to see it in JMRI. It's not going to do much interesting things as an OpenLCB node, but you will see whether it's there. So it will be fully standards compliant. It's just going to do nothing more. So that's basically how you get started, and really the simplest sketches that are in the examples are this is it. There are a couple of extra lines where you set like the node name and the hardware version and software version, which the node is going to be then report to JMRI. I have skipped those few lines here. So that's the basics of OpenMRNLite. Now let's take a look at actually doing something more interesting. So for the next section of the talk, I'm going to talk about how do you interact with events if you're using OpenMRNLite. In general, I mentioned that, well, we're just instantiating objects in the global namespace. So here we are just going to be instantiating producer and consumer objects. The first thing that we need to do here is that for the pin numbers, we have to tell OpenMRN what kind of pins they are and what do they do. So I have this GPIO pin shortcut. This is inherited from actually through OpenMRN. The reason why this is pretty helpful and useful is that you will have the ability, and Robert Heller has some great examples of this, to deal with let's say pins that are on an IO expander like an MCP 23017 expander. You have the ability to deal with those pins the exact same way as you would do with the normal set of pins. So somebody has built me a board with 4 of those MCP 23017 on one board. So I plugged that board in, and I immediately get, I don't know, like 64 IOs or something, some crazy number of IOs. And you can even daisy chain them. I think you can daisy chain like 2 of them. You can have 128 IOs on a single OpenLCP node. And through this GPIO abstraction, that actually becomes possible. So here we have a producer and we have a consumer. The way to instantiate these objects is a little bit complicated. But what's going to happen is that this is going to be doing actual debouncing of the input. So if your input is flip-flopping, it's going to wait for it to be at a steady level, and you basically just tell it what kind of event IDs it should be listening for, what kind of event IDs it should be producing, and then it will automatically go to the described GPIO. And user button and LED built-in, these are basically pin numbers. Like one of them is 9, the other is 13, I think, on the particular Arduino core. That's it. In order to do the debouncing, we also have an extra object that basically just performs the polling loop so that you don't have to worry about that. And once you've instantiated these objects, you can basically like sit back and relax, and the OpenMRN stack is going to do everything for you. So it's going to basically be listening for these events, and when they come, it's going to turn the LEDs on and off. And whenever you press the button and the debouncing period has elapsed, it is going to be producing those events and sending them to the bus. It's going to take care of everything necessary in addition for the standard compliance, the event identification, the routing, etc. So this is a great and very, very simple way to get started. I have actually built like an entire layout based on these. And then the trick that I employed is that I basically just computed the event IDs from whatever the node ID was. So if I had the node ID ending at 22, then I basically computed the event ID to be like 220001, 220000, 220003, 220002. So this way, I basically built a number of I/O boards, and I basically just installed them into the layout, and I knew exactly what kind of events are coming from there. So this is basically creates a fixed layout of event IDs for the particular hardware, or well, for the particular sketch that you download. I have a lot more interesting event handlers. Well, these two are actually event handlers, the poll producer and the bit event consumer. These are event handlers. I have a number of additional interesting event handlers. The very simplest ones, the ones that you've seen, these basically take 2 events, so they do on and off. This is like the very classic thing. With the simplest bit event producer, you actually have to call a function on it for it to produce the event. The poll producer, which I showed previously, that actually performs the polling loop. So it watches the GPIO periodically, and it performs the necessary debouncing, and then it produces the events automatically. So you can create it once, and then you can forget about it. The next that is pretty interesting is the network initialized bit. So this is still a bit, so it has 2 events on and off. but it is designed to basically listen to somebody else's state. So like a great example for this would be you have like a signal node, and you want to know the occupancy ahead of you. And that occupancy might be coming from a different node. So for the occupancy, you have an occupied-unoccupied pair of events. But now what you want to ensure is that when you actually start, that you actually query the state of the occupancy. And then when the incoming status reports come in, the event status reports, that those incoming status reports get then processed by your node. And the network initialized bit actually does this. So it listens to one bit of state via on-off events, and it sends out the query, and then it listens for the responses, and then keeps track from that point on. And it even lets you know whether it knows the state or it doesn't know the state. So, for example, if you are building like signal logic, then you can, for example, make your signal fall to an absolute stop if the occupancy information from the block ahead of it is not available, or maybe emergency stop or blinking red or whatever is appropriate for your signal system for like signaling a malfunction. So you can write that code very, very simple using the network initialized bit. Then more interesting event handlers. I have the bit range, event producers and consumers. So these work with multiple bits in one go. That is helpful if you don't have an awful lot of memory, or you don't want to just like copy paste the same code many times. So if you have I don't know, like 10 bits, then it takes like 20 consecutive events, and those 20 consecutive events always set like the next bit on and off, and the next bit on and off, and the next bit on and off. And then whatever is happening, whatever you get from the network, it basically just gets written into a memory variable. So it basically shows up in your RAM. And then from that memory variable, you can then write it into GPIO, or maybe the memory variable gets shifted out to a shift register. That's actually a very simple and easy to do use case. Or you could even put your memory variable into the GPIO register if it's an output. If it's going to be input, like you want multiple block detectors ahead of you, that also works. Or maybe you just write a function in your loop that deals with those multiple bits. Then the next one that I have is the byte range event consumer or producer. This allows you to get entire bytes via OpenLCB events. So basically, when you have an OpenLCB event ID, it basically takes the last byte of that event that came in and then puts it into a memory address for you. So you basically have a byte array, a uint8 array store, and then you tell it what's the count, and you tell it what is the starting event. And then it basically puts like count times 256 events from there, and then whichever byte came, it basically is written into the store. So you can use this to have I don't know, like signal aspects, for example. Yeah, that's what I used it for. I used it for signal aspects, but I even had like interesting abuse of it, like the brightness of some lamps. I have recorded as these like 256 events. So I could basically just like send out an event with a particular like last byte, and then it would change the brightness of all of my signals. I had actually done that. Even more interesting event handlers. We have the DCC accessory producer, and then a matching consumer. These are controlling the DCC turnouts. Either any DCC turnout or all DCC turnouts, because you basically just say turnout number, normal or reversed. So these are always producing the well-known events, which are part of the standard. So if there is an LCC command station and you use the DCC accessory producer, the thing will eventually end up sending out a DCC packet to the track. So if you have a DCC accessory for controlling turnouts, and you have an LCC command station, this is how you would do that. This is particularly useful for a throttle, because if you have a throttle and the throttle has like a number pad, in the number pad you type in turnout 37, normal, and then the DCC accessory producer takes care of that. There is a matching counterpart, the consumer. This one is consuming the well-known turnout events. So basically the same set of events. This can be used in pairs. Very useful for a command station, but of course you can build it in anywhere you want. And the real bonus is if you build it into one of your nodes, you can actually use a throttle at that point, and then you can use the throttle to punch in a turnout number, like turnout number 72, and then your node is actually going to get that particular event. So you can trigger your node from the throttles used by punching in numbers this way. And any LCC compatible throttle is going to be triggering that particular event. Even more interesting event handlers. I have the callback event handler. This is really good for writing logic statements. So for example, I want to listen to these and these occupancy events, and I want to produce a signal aspect event. And with the callback event handler, you can write this in straight C code and do all of that. And it's basically going to call your callbacks when the consumed events come in, and you have the ability to send out your produced events and write basically logic for your railroad in C code, which is for many of you probably a lot more straightforward than using some of the commercial options for creating logic, like either the macro engine in the TCS command station, or the logic blocks in the railroad circuits devices, or this logic Q language that Dick Bronson has invented for his newest thing, which looks like a relay ladder thing. So this is probably a separate talk by itself on how to write logic for a railroad using an Arduino sketch and the callback event handler. We can probably come back to that if there is some interest, and I can write some examples in order to illustrate it better. I'm not done. I have even more interesting event handlers. The configured producer and configured consumer. These are like the very simplest bit on and off event handlers. The producer is also polled automatically. These are interacting with GPIOs directly. But the most important aspect of that they actually come with configurable event IDs. Everything that I have showed until now, you have to put the event ID into your code. So in the C++ code, or in the Arduino code, at some point you create the object, and at the time when you create the object, you set the event ID, what the object should be. Now the configured producer and configured consumer have configurable event IDs, and these come with the integration with the CDI standard. So that is the place where you can create, the classic style input-output nodes, where you have a generic node, and then you go to JMRI, and then in JMRI, you actually configure the node for whichever event IDs you want. So that is really the classic I/O board. Everything else is just hard-coded event IDs. And you can build a layout from hard-coded event IDs. It's going to work very well. You can build a layout from hard-coded event IDs and commit all of your source code into version control systems like GitHub. And that way you can make sure that your layout actually has a record of what is actually happening. As a software engineer, I find that extremely appealing. The JMRI-based configuration, obviously, that is point and click and copy paste and nice UI-based, but you never really have a record of what's happening. So the configured producer consumer allows you to do that, the classic way. And then there is one extra one, the configured pulse consumer. which actually does not have 2 events. It only has 1 event. But it is configurable with CDI, and it's going to emit a short pulse on the matching GPIO. You would basically need these if you have coil drives. So like magnetic double coil or something like that, something which is required to have a short amount of pulse, otherwise it burns up.